So it turns out there's an interesting relationship between a function and its inverse with regard to the derivatives. And so that's what we're going to explore here in this video on derivatives of inverses. So as an example, I have two functions which are inverses of each other. I have x squared on the interval 0 to infinity, and I've got its inverse, the square root of x. So first thing we should notice is that the point 2, 4 is on the graph of f, which means that the point 4, 2 is on the graph of its inverse. What we're interested in is the relationship between the derivatives at these moments. So let's calculate the derivatives of each. So f prime of x is going to be 2x, and the derivative of f inverse is going to be, well, if I write root x as x to the 1/2, then I can see that it's 1 over 2 x to the negative 1/2, which is the same as 1 over 2 root x. So now what I want to do is I want to plug in 2 into my derivative of f so that I can find the slope of the tangent line at x equals 2. So the slope of that tangent line. So that would mean I'd have to plug in 2. F prime of 2 equals 2 times 2, which equals 4. And then I'm also going to calculate the slope of the tangent line at its the corresponding point over at the inverse here. So the corresponding point I'm calling 4, 2. So what's the slope of this guy? Well, let's plug 4 into the inverse derivative. So that's 1 over 2 square root of 4, which is 1/4. And so you may notice that these two slopes are related by being reciprocals of each other. And that's not too much of a surprise if you think about how inverses relate, right? The x and y coordinates swap, which basically means that, let me record this here, which basically means that if you're dealing with slopes, on our original function, our slope is change in y over change in x. But in its inverse, that relationship's going to switch to change in x over change in y, right? So like x and y swap, which basically means that in the inverse, change in x's become changes in y, and vice versa. Okay, so let's just record what we've noticed, and then we can prove it in the next slide. So the slope, I want to write the slope of the reflected tangent line. Now I say reflected tangent line because another thing we know about inverses is that they're reflections of each other over the line y equals x. Right, so you can think of this tangent line as being reflected over the line y equals x to produce the one on the right. The slope of the reflected tangent line is the reciprocal of the original. The reciprocal of the original. So this will come in handy if you're given the derivative of a function at a point, and you're asked for its derivative, the derivative of its inverse at its corresponding point. You can answer it quickly if you remember this relationship. It's just the reciprocal. So let's prove it on the next page. So here I've formalized what the theorem we came up with, or we've noticed. If f is differentiable at every point of an interval I, and f prime of x is never 0, so I should have mentioned that in the last slide. The reason we don't want f prime to ever be 0 is because if f prime is 0, we have a horizontal tangent, right? And that means that the inverse, since x's and y switch, would have a vertical tangent at its instant, and that would mean the derivative wouldn't be defined, so the inverse wouldn't be differentiable. So we need to state that f prime can never be 0, because we don't want the inverse to have a vertical tangent. then f has an inverse, f inverse, which is differentiable at every point on its interval, f of I. And furthermore, there's a relationship. So if f of a equals b, we know by properties of inverses that f inverse of b equals a, and the inverse slope relationship is what I'm going to call it. The inverse slope relationship that relates the derivatives is that the derivative of the inverse at b is 1 over the derivative of the original function at a. So let's prove this. So the proof is going to be pretty quick. I'm going to say, let's let f of a equal b, and its inverse, therefore, would produce a when we input b. And I'm going to use a property of inverses, which is that when you compose them, f of f inverse of x equals x. And that's a property of inverses. Right, if you input a function in the inverse, it gets sent to an output, and then you input that output back into f, you're going to get right back to where you started. And now I'm just going to use I'm going to take the derivative of both sides of this equation. So the derivative of the left side requires that I use the chain rule. So it's going to be f prime of the inside times the derivative of the inside. And the derivative of x is just 1. And so now what I'm going to do is I'm just going to solve. I'm just going to solve for this guy. So that means that f inverse prime of x is equal to 1 over f prime of f inverse of x. Okay, so far so good. Now all I'm going to do is I'm going to plug in b for x. So that means that f inverse prime at b is equal to 1 over f prime of f inverse of b. But f inverse of b is just equal to a. So this tells me that f inverse prime at b is equal to 1 over f prime of a. All right. So again, stated informally, we would just say that the derivative of a function at a certain point is equal to the reciprocal of the derivative of the inverse of that function at that mirror point, or the corresponding point.